Hello, I'm Brian Joseph. I'm the moderator for today's event. This is the Aberlin ao Vivo Linguists Online series. It's an initiative of the Brazilian Linguistics Association and is designed to give students and researchers free access to state-of-the-art discussions on the most diverse topics related to the study of human language. Our speaker today is Andrea Sims of The Ohio State University. Andrea is a colleague of mine and a collaborator, and I have to say this as well, though it will embarrass her, a former student of mine. But she's now a rising star in our field, especially with regard to morphology and morphological theory, with work on especially the Slavic languages, but other languages as well. She has a book with Cambridge University Press from 2015 on inflectional defectiveness, and a widely used and widely read textbook on morphology that has already been translated into a couple of other languages. The importance of the title, I'm sorry, I muted myself by accident. Thinking locally, acting globally, the importance of localized analogy for the emergence of morphological organization. And I'd like to thank Andrea for her participation in this event, and to remind all of you out there that questions can be asked in the chat, and we'll have discussion at the end. So thank you, Andrea. Please take it away.
Okay, thank you very much, Brian, for that lovely introduction and for serving as the moderator today. And I'd like to thank the Brazilian Linguistics Association, Aberlin, and its partner associations for this opportunity, and Miguel Oliveira in particular for the invitation and for doing the coordination. This is a great resource. This series is, Aberlin ao Vivo is a wonderful series of lectures, and I've really enjoyed following it along these last several months. And I'm very happy now to get to be a part of it. Okay, so as Brian said, my talk today is called Thinking Locally, Acting Globally, the Importance of Localized Analogy to the Emergence of Morphological Organization. Okay, so I'm going to start with an allegory that is fairly well known. It goes back to sort of ancient times and a Greek poet, but was brought into better understanding and better widespread fame by Berlin's book in 1953 that has this allegory of the foxes and the hedgehogs. Okay? So foxes are predators for hedgehogs. Okay? And the point of the allegory is that foxes are very creative in their approach, that they will explore many ends and approaches to getting the hedgehog, but that the hedgehog really only has one defense mechanism, namely its spines, to keep the fox at bay. And we can see this as sort of an allegory of intellectual personality, right? Where the fox is interested in the details and the particulars, in the marginalia, as Berlin says, seizing upon the essence of a vast variety of experiences and objects for what they are. Whereas the hedgehogs of the intellectual world have a desire for a single universal organizing principle to their theories, and see with a relatively narrow vision, but try to unify everything within that vision. And in morphology, Mark Aronoff points out in his paper in the Cambridge Handbook of Morphology that the morphological systems vary greatly in the extent and type of their complexity, making morphology a particular playground for foxes. So for those of us that are interested in the particulars, in the details, and in what are arguably the marginalia, Jenny Audring, in her series on her lecture on unproductive morphology in this same series, declares herself a fox, as does Mark Aronoff, and argues for looking for ways for foxes and hedgehogs to communicate better. And in that spirit, I'd like to offer this talk about ways that we should look for communication between foxes and hedgehogs, and in particular, ways that foxes can contribute to the questions that might be of interest to hedgehogs. Because as Mark points out also, the downside is that foxes may be satisfied with smaller pickings and be less focused on or even interested in the big picture. And I will argue that we should be interested in the big picture, and that the focus on details can offer a lot to the large picture. Okay. So to see what I mean by that, I'm going to sort of switch my metaphors here real quickly and show this sort of time series of pictures that was taken in Paris of a sort of public plaza space. And you can see that at the initial photograph, there's just a series of people wandering around. But then a couple minutes later, there's this circle, and you can imagine and probably guess that the reason for the circle is that a street performer has set up and people have gathered around to watch. Likewise, you can see a couple minutes later an emerging pattern where another street performer has set up, and a minute after that, here's another circle. And we can ask questions like, what is the cause of the circle? Well, it's diachronic in nature. The circle can be viewed as a synchronic object, and the structure emerges over time. It is a response to environmental pressures to maximize each person's view of the street performer, to minimize obstruction of the view of neighboring people, and to adjust to accommodate more or fewer people. So a circle is a wonderful structure for getting many people into the space in an optimal way. Ultimately, the circle is the unintended consequence of individual actions. Each person interacts only in a local way with surrounding people. There's no top-down imposition of the structure. We can view it synchronically, but it has diachronic causes. And importantly for the point here, each person interacts only with the people surrounding them, and yet this global structure does emerge. So we need to focus on both the local level and on the global level in order to understand fully the structure going on here. So I titled this talk, Think Locally, Act Globally, as a play on the environmental slogan, think globally and act locally. And I'd like to sort of flip that around, because I think that there is evidence that speakers think locally, but that we should also question how those, the results of that local thinking produce actions that are global effects on morphological systems. So for this, I will take from my mentor, Brian Joseph. As he pointed out, I'm a former student of his, and I follow him very much in thinking that most generalizations in morphology and in linguistics in general should be recognized as being truly local in nature. That is, they have a restricted scope, and where linguist generalizations go astray is in not being sufficiently localized. In other words, speakers think locally. So we want to think about the consequences of that. We as foxes should focus on the big picture, how speakers' local thinking acts to shape morphological systems at a global level, not unlike how people gathering around to watch a street performer form a circle. What is sort of the bigger consequence here? What is the equivalent of the circle in morphological systems? And the reason we want to ask this is that there actually are quite a number of hedgehogs out there. And one popular line of thinking about sort of global structure emergence has to do with learning biases and other sort of functional pressures in linguistic systems. So here I just take one single example from Sarah Finley's work, where she says that relative ease of learning is reflected in the typology of linguistic systems. And however true that may be, it's also the case that much of this work, by virtue of being sort of hedgehog in its focus, being interested in a unified understanding and seeking out a unified understanding of morphological emergence and typological generalizations overall, has been not that focused on the details, the particulars, and the marginalia. And I would like to argue that we need to sort of refocus on that, and that this is a productive area for foxes and hedgehogs to communicate. So to preview what'll be sort of the bigger point at the end of the talk, more precise quantitative tools for describing inflectional organization can offer better insight into how words interact in that local way, but also in the context of learning biases and other pressures. So this is where the focus on the local meets with the focus on a unified understanding. Ultimately, this has implications for morphological generalization, learning, change, and emergent structure. And that we need to pay more attention, therefore, to these local interactions when investigating typological patterns and emergent morphological structure. I think this is an area where historical linguists have long been focused on the contexts for change, but much of the work on emergent grammar has been more hedgehog in its focus. So an outline for the remainder of the talk, we're going to look at some examples of what I mean by thinking locally. Then we're going to look at some examples of what the effects might be globally, acting globally, and then connect the local to the global. I'm going to show results of some sort of ongoing and preliminary work using computational modeling. So first, thinking locally. So coming back to this idea that speakers think locally, what do we really mean by that? Well, a case that might be familiar to many people has to do with the English past tense, where there are, in addition to regular past tense patterns with suffixed ed, spelled ed, there are a wide variety of patterns of vowel change in modern English. And much work going back to at least Bybee and Motor 1983 argues and shows that there is limited productivity of many irregular past tense patterns, and that this generalization is really local in nature. So that by which I mean, it depends on phonologically defined lexical neighborhoods, also called lexical gangs, and type frequency. So looking in particular at one pattern, which is the one that has in the past tense, okay, like ring, rung, hang, hung, and strike, struck, one thing that we can observe is that there's a sort of phonological generalization to be made about the past tense forms, where they have either a velar nasal or a velar oral stop, often in the past tense, among other aspects of the neighborhood, and that this sort of phonologically defined gang has in fact over time drawn other words into the pattern. So cling, spring, dig, stick, and string all had periods of having either a different past tense vowel change pattern or a regular past tense pattern, and that they've all sort of moved into this pattern at one point or another. The details are very various historically, right? And so this sort of irregularization of morphology, as it's often talked about, really is a function of the fact that these words belong to a phonologically defined neighborhood, and that the local neighborhood is influencing their morphological pattern and creating this low-level productivity for the irregular pattern. In my own work, I've shown that this also extends to patterns that might be surprising. For instance, inflectional defectiveness. Brian mentioned this book at the beginning in his introduction. And so in Russian, in the present tense, present and future tense of perspectives, excuse me, there are 3 person and 2 number values, typically, as we see in the verb for sprosit. And in the verb for convince, however, there's no first person singular form. Speakers simply do not want to say, I convince you with this verb. They will go around it with some sort of circumlocution instead. And there is basically a gap here, right? That there is no paradigmatic form for this cell. And in work that I've done with colleagues Robert DeLand and Janet Pierre-Humbert, we looked at the neighborhood structure of those paradigmatic gaps and saw that they cluster pretty strongly around stem final consonants that are palatalized D, and then the relative likelihood of having a gap goes down as you sort of move out from that in sound in phonological space. And modeling this phonological neighborhood effect computationally, we built an iterated learning model and showed that when the model is sensitive to morphophonological neighborhoods, it'll in fact learn defectiveness across a fairly wide space of frequency of verbs. But when it's insensitive, when information about the phonological neighborhood is withheld in the model, it'll in fact only learn defectiveness, they'll only learn the gaps in the most high frequency words. And so what we can draw from this is that gaps are learnable across a wider frequency range because they are supported and reinforced by their phonological neighborhood. This was sort of the core conclusion of this work. And so we can see that in many different ways, including in defectiveness, the relationship between a target word and its neighbors is central to the generalizability of inflectional patterns to new words. By extension, morphological change is driven by small-scale local generalizations. And this is consistent with morphology being synchronically more idiosyncratic and morpholexically specific in nature compared with phonology and syntax. And this is particularly why, as Mark Aronoff pointed out, morphology is a particularly great home for intellectual foxes, myself included. But we don't want to simply stop at the local level, right? We want to move beyond thinking locally to looking at sort of the global results, so acting globally. So let's look at that for a minute. So this question of phonological neighborhoods is really about predictability of form in a sense. And here we can switch to think about the nature of that informativity. So if we take this example from Russian noun classes, this is connected to a problem that has been called the paradigm cell filling problem by Ackerman et al. In 2009. And in Russian, if you encounter a word that you've never observed before, a nonce form or a wug, okay, and it's in the accusative singular and it has the ending u, it ends in u, that actually is very informative because, as you can see from the distribution of classes, it must belong to class 2. So that's the only class that ends in u in the accusative singular. However, if the form of the word that you observe is om and it's instrumental singular, well, that's somewhat informative. It narrows the space to a choice between 2 classes that are related to each other. If what you get is the dative plural, well, you're sort of out of luck in terms of predicting what class the word belongs to and what the other inflected forms of the word are, because that in fact could belong to any class at all, because the dative plural in all classes is in fact So we can think about this as sort of central to the problem that part of the way speakers might solve the paradigm cell filling problem is by looking at words that are locally similar to them and trying to predict what the other forms are, and that sometimes this information will be easy and sometimes this information will be difficult. So it's easy if it's oo, and it's hard if it's So we can think about this as a question of the network structure. So I'm going to propose to think of inflectional systems as networks. Here, taking a toy example, just to show what I mean by a network, we can see that there are 3 classes represented on the right by 3 nodes, that there are edges, which are exponents that those classes have in common. So here, all 3 classes in cell Z have suffix F, that's the equivalent of in the dative plural in Russian. And so the edges, the lines, connect those classes by virtue of having this shared morphological structure. We can also think of these edges as being weighted, that classes that have more forms in common have a heavier weight. And we can think of there as being node size, which is not actually shown in the figure on the right appropriately, but we can think of there the number of words, the type frequency of the class, as being the sort of size of the node. So the more words there are in the class, the bigger the node. And taking this idea of a network and applying it to Russian and other languages, we find actually that there's a lot of diversity from one language to another. So here we see 3 examples. So I'm just pulling out illustrative examples of French verbs, Greek nouns, and Icelandic verbs. And we can see that these all have some properties in common. They're relatively sparsely populated with edges, and those edges have relatively low edge weight. So the edges are colored according to their weight. So the darker the edge is, the higher the weight is. So the more those 2 classes have morphological forms in common. is darker. And this is a situation that corresponds to high implicative structure in the terminology of sort of the morphological complexity literature, the literature that's been interested in the paradigm self-filling problem. Because classes that are not connected are more distinct. And if classes are more distinct, any single form that you observe from that of a word from that class, the better you are able to predict all the other forms of the class. So more distinctness, which is to say sparser population of edges in the network, means better predictability. And so we see here French, Greek, and Icelandic. We can compare that to newer Seri and Voro, where we have clearly networks that are much more densely populated with edges and have higher edge weights, which is to say darker lines in the graphs. And this corresponds to much lower implicative structure, which is to say if you get one inflected form of a word that you've never observed before, your ability to predict the other inflected forms is much reduced because classes overlap so much that getting a particular form does not generally reduce the space, the hypothesis space that you have about what class it belongs to, certainly not very much. And it's been argued by Behrman and colleagues that in fact, this exact set of languages are ones in which there is predictability syntagmatically, so specifically based on the stem shape or based otherwise on morphophonology, so that you're not essentially you're not relying on predicting one form from another on the paradigmatic dimension. You're instead able to predict from the form that you get on a syntagmatic dimension, something that's not directly represented in the graph. So these may be able to be more complex in the ways classes overlap as a result, is the idea. Finally, we can come back to Russian nouns, okay, Chinantec verbs and Kadiweu verbs, where we see that these are neither densely nor sparsely populated with edges on average, but that compared to the previous graphs, what we have is sort of dense subgraphs and a lot of clustering. So we earlier described Russian nouns, I had described Russian nouns as having 4 classes, but really if we take all of the patterns of exponents in Russian nouns into account, for example, there are stem alternations, there are stress alternations, there are alternate endings. Then what we actually get is a much larger number of classes, something more in the order of 87, but they cluster very tightly. So really what we have is a few macro classes with some variation internally to them. And that shows up in this kind of network structure as clustering. So we seem superficially to have some different types of network structures. And this is really interesting because it's not a view that we can get from the low-level sort of close-up understanding of the paradigm self-filling problem, or more generally from a close-up investigation of factors in morphological generalization of the kind that foxes tend to prefer. We can see that this also makes, this is important for understanding what's going on at the local level. So if we take those graphs that we've just seen, I built a regression model that predicts the average conditional entropy. So you can think of, if this isn't a familiar term, you can think about this as the complexity of the system or the unpredictability of the system as a function of properties of those networks that we just saw using sort of standard metrics from graph theory. And in particular, what I'm showing you on the right has to do with degree. So degree is the number of edges a given node has connected to it. So if we take a single node here, we can see that there are 2 edges. So we would have a degree of 2. We can take the average across all of the nodes, the number of edges that they have connected, as a measure of the density of the network. So all else equal, higher degree means a more densely populated network, one with a lot of edges in it. Okay. And what we can see in the graph on the right is the coefficient, okay, for degree as a predictor of complexity. And what you can get out of this is that in networks sparsely populated with edges, having more overlap with other classes actually makes the system more complex, which is to say less predictable. So in French verbs, the classes that are relatively higher in number of edges, okay, the nodes that are relatively higher in number of edges, create a lot of unpredictability for the system as a whole. In contrast, in networks that are densely populated with edges, there's a negative relation, an inverse relationship between degree and complexity. So in networks that are densely populated with edges, more overlap with other classes, in fact, makes it less complex, which is to say more predictable. And for many people, this is the unintuitive result. Okay, why should classes overlapping more help with predictability? And the answer is that when you get past a sort of threshold point in the network where your classes are so densely connected with each other, that in fact what you're looking at is a series of essentially similar classes that differ only a little bit. And so if you get any one form, chances are, and you need to use that to predict other forms, chances are that in fact, that's going to work for you because essentially they're the same class with minor deviations. And so if you're predicting one form from another form, there's a good chance that they behave like they are the same class in those regards. So the point here is that it matters how languages, how nodes are interacting with each other, which is to say how interactions happen at the local level. Inflectional systems differ substantially in network structure overall, as we've seen. And this is an area I'm still working on to understand exactly the range and dimensions of that variation. But even from the illustrative examples, we can see substantial differences. And that network structure offers a basis for typological classification rooted in the interpredictability of inflected forms in a way that's directly connected to this paradigm self-filling problem and more generally to the local nature of morphological generalization. But it allows us to quantify the ways in which those local relations, the local view of morphological generalization, is similar or different on both a language internal and a cross-linguistic basis. And in particular, generalization works differently on the local level, depending on how words are embedded in their networks. That's the important view here. And this is why we have to take a view, even if we're interested in the details, the particulars, the marginalia, we have to take a view also of the global, because the global affects those local interactions, and those local interactions affect the global structure. Okay, so I have more about this in a paper that I wrote this year for anybody who might be interested in that. So that's why we need to think about the global and not only the local. And now finally, in sort of the last sort of section of this talk, major section of this talk, I'm going to try to connect the local to the global sort of more specifically by seeing how global structures might emerge, testing hypotheses about how global structures might emerge from purely local interactions of the sort that we saw in the first section. So here I'm going to present a preliminary look at one particular emergent pattern. And this is work that I've been doing with Jeff Parker and Rob Reynolds, now both at Brigham Young University. And in particular, we've been looking at this pattern that's been dubbed marginal detraction by Stump and Finkel. So what they say is that marginal inflection classes tend to detract most strongly from the inflection class predictability of other inflection classes. So here marginal means really low type frequency, which is often equated with irregularity, but really we'll try to stick with low type frequency as our definition. And the idea is that low type frequency classes cause more problems for this paradigm self-filling problem for predicting the inflected forms of a previously unobserved word than high type frequency classes do. Okay, so low type frequency classes cause more problems for predictability of the system than high type frequency classes do. So looking at those 9 languages that we were just investigating the structure of, we can ask whether they have this marginal detraction pattern by looking at the relationship between the type frequency of the class, which is node size in graph theoretic terms, and what we're calling entropy difference. Okay, so the x-axis here is the log of the number of unique words that belong to an inflection class. Each dot in the graph is an inflection class. The y-axis is a measure as average conditional entropy. So essentially you can think of this as average unpredictability, if this is if entropy is unfamiliar to you, where we've calculated the average conditional entropy of the entire inflectional system, and then removed one class and recalculated the average conditional entropy of the whole system, and then calculated the difference between those two numbers. And so what you're seeing on the y-axis is the difference between those two numbers. And we iterate through all of the classes so that the number for each dot represents is the contribution of that class to the unpredictability of the inflectional system uniquely. Okay, so it's unique contribution to the complexity of the system in this sense. And so when we have the marginal detraction pattern, that comes out as a negative slope. So what that means is that, for example, in Genentech, low type frequency classes, so classes with very few words in them, disproportionately create problems of prediction. So they are contributing more to unpredictability. They have higher values on the y-axis on average than high type frequency classes do. So negative slope here is that particular pattern where low type frequency classes cause problems for prediction. And we can see that that is true in this graph in Genentech, Icelandic, Kadeweu, Newer, Russian, and Seri. French and Greek both show trends in the opposite direction, but not ones that are significant. Voro shows a trend in the same direction as the other 6 that have marginal detraction, but again is not significant. Okay, so we see that the generalization made by Stump and Finkel that marginal classes tend to detract most strongly from the inflection class predictability of other inflection classes is substantiated in this set of languages, but not universally. It is 6 of 9, with 1 more trending in that direction. So what we want to do is model the emergence of that marginal detraction pattern. So the core intuition that my collaborators and I have been pursuing is that analogical pressure is really about the inflectional system. It's really about patterns of shared inflectional exponents. And so while there's this tendency to focus on low type frequency classes as irregulars, as things that are sort of preserved because of their high token frequency typically, and as sort of marginal to systems in this regard, we really want to shift this focus from the properties of individual words and their token frequency to how those words are embedded in their inflectional network and interact with each other locally in the context of learning biases. So we want to connect that local to global. So to do this, we built an iterated learning model. So just a quick introduction to iterated learning for those of you that may not be familiar with it. In iterated learning, it's a computational model where there are 2 types of what are called agents, adult agents and child agents. And we have the adult here on the left and the child on the right. And the adult talks and the child listens. So the goal is to express some meaning, and the adult has a lexicon of possible ways to express M. We can think of these in morphological terms as, say, affixes A and B, and has some knowledge of the probability over A and B. So here a probability, say, of A being 0.25 and B being 0.75. The adult has this sort of lexical mental representation, and in our model, every agent, there are 50 agents in every generation, every agent has their own mental lexicon. Productions are sampled from that grammar, from that sort of lexical knowledge. The child agent hears the productions, applies a learning algorithm. Okay. The child then becomes the new adult. New children are born. The goal is again to express some particular meaning. Let's call it M here. Productions are sampled from the grammar. The child agent hears the productions. The child agent applies the learning algorithm, and so on and so forth, and you run it out over multiple generations. So this is essentially a metaphorical game of telephone, this children's game of telephone, where children whisper in each other's ears in a sort of in a chain, with the point being to see how the message mutates over the course of from the beginning message to the end message over the course of being whispered from ear to ear to ear. The learning algorithm that's applied in our model is Bayesian. So there's a likelihood which encodes observations. The more observations the child has, the less it is reliant on predicting a form, the more it'll simply replicate the form that it has observed. The prior encodes learning biases. So when there's insufficient data observation to fully predict a form, the prior has greater weight and encodes the learning biases. In our particular case, the prior probability of a hypothesis H for a target lexeme A and paradigm cell X, so for some particular form, is determined by the mean observed behavior of lexical neighbors that overlap with A and some other cell Y. So this is coming back to the idea that generalization is local, okay, and that local words, so similar words in the lexical neighborhood, will influence the productivity of a target word. So that's encoded for us in the prior. And notice that that means that within our model, there is pressure towards similarity to neighbors, but not pressure inherently towards simplicity, particularly because every inflected form is being predicted separately from every other inflected form. So it's not whole classes being moved in any particular direction. And it's possible, and in fact does happen in the model results, that classes can split and sort of shatter into multiple more specific, larger number of more specific classes as sort of mix and match forms. Children hear from multiple adults, so the productions can be different from different adults. And this means that over the course of the model, it's possible both because of this effect of the neighborhood that influences the prior and because of observations from different adults, that the child's representation and the adult's representation can differ. Okay, so there can be morphological change within the system from one generation of the model to the next. So in our particular model, we seeded it with 1,000 lexemes, each of which had 6 paradigm cells. This is an artificial grammar situation. We modeled type frequency based on the type frequency distribution of Russian. So some classes had lots of words in them, and some classes had very few words in them. But crucially, we kept the token frequency of lexemes and paradigm cells flat. They all had the same token frequency, in particular because we wanted to look at the effect of network structure, of the way words were related to each other on a local level. We want to look at that effect and hold, therefore, token frequency constant. So remember that we can think of this as a network. These 1,000 lexemes with 6 paradigm cells can be organized into a network structure. Specifically, we were interested in network density. As we saw in the previous section of the talk, network density seems to really affect whether overlapping with another class facilitates prediction of inflected forms or inhibits prediction of inflected forms. This seems to be a major factor of network structure that influences local interactions. So we built 10 input systems where what you're looking at here is the equivalent graphs for those input systems, where each class contributes the same amount of system complexity. So each node overlaps with the same number of nodes as every other node and has the same weight on average. And you can see that input 1 is simply each class is connected to 2 other classes, overlaps in morphological form with 2 other classes, and it ranges up to input 10, where every class overlaps with every other class in a substantial way. So we're looking at network density here, where we have the lowest density in input 1 and the highest density in input 10. And some results of the output of this across the course of 10 generations was that more classes overlapping in the input led to more clustering in the output. So remember that the classes looked like this on the input, but on the output, they look like this. So when the input degree was 2, which is this situation here for input 1, then what you get is sort of a breaking up, sort of a maintenance of loose connections to other classes and perhaps a little bit of breaking up of the structure, but not the kind of clustering we observe when the input structure started with a degree of 6. So here we see some emergence of different patterns where clustering emerges from some structures and not from other inputs. Edge weight here also matters, so the number of paradigm cells in which two classes overlap makes a difference for the output as well. When there are more cells overlapping in the input, there is a less connected network in the output. So here we have the same structure where when we have a degree of 2 and an input weight of 2, we end up with this structure we see on the left. When we have a degree of 2 and an input edge weight of 3, however, classes tend to break apart, which is to say, from each other, which is to say they become more distinct. So in fact, the graph on the right is better for inflectional predictability than the graph on the left, because classes lose connections that they have to other classes. If they're more distinct, they're more predictable. So coming back to this issue of, those are general trends in the model, coming back to this issue of marginal detraction, we can look and see whether marginal detraction emerges within the model. Remember that there was no pattern of marginal detraction in the input. So any marginal detraction found in the output is a function of the way that the networks interact, elements in this networks interact with each other in the context of learning biases. And in fact, we find that we do get marginal detraction in some of the outputs, particularly datasets 1, 2, and 3. So this is the same type of graph we saw earlier, where we have the type frequency of the class, log type frequency of the class on the x-axis, so the number of unique words in the class. And on the y-axis, we do the same kind of entropy difference calculation, where we're calculating the average conditional entropy, so the average unpredictability of an inflectional system, removing one class and calculating it again, and then taking the difference between the two. So again, negative slope here means marginal detraction. We can observe that while there are a couple data sets, namely 4 and 5, that are trending in the direction of marginal detraction, we get one class that in fact significantly moves in the opposite direction. So in data set 7, the high type frequency classes actually detract from the predictability of the low type frequency classes more than the reverse. So this is a little strange from the perspective of irregularity. We're used to thinking of irregularity as causing disruption to the system. But in fact, in dataset 7, what emerges is high type frequency classes, so quote, regular classes being disruptive to the system. So these were the ones from our inputs that produced marginal detraction in the output. These are the ones where we got no marginal detraction in the 10th generation, although they were trending in that direction. And then as we get to more density, they either collapsed or, in the case of input 7, produced anti-marginal detraction in the 10th generation. So the ones that are not shown are ones where they collapsed to a single class or to 2 classes, which isn't enough data to be able to investigate the question of marginal detraction statistically. So these model results suggest that marginal detraction is an emergent property of inflectional systems that plausibly, at least, derives from how words are embedded in inflectional networks and how they interact locally with each other. Okay? So learning biases certainly matter. The model encodes the idea of local interactions, okay, in the way that we saw with the English past tense or the Russian paradigmatic gaps. But that is held constant across the different input models. And so it cannot explain the differences in learning biases, cannot by themselves explain the differences that we find in the output, particularly whether marginal detraction emerges or not. Frequency also matters, but it is held constant across the conditions. So the token frequency of words here cannot also be sort of blamed or credited with the emergence of marginal detraction. And so this is a proof of concept illustration, ultimately, of the importance of the ways words interact with each other in local terms, but that those local interactions differ significantly depending on the, in this case, density of the network in which they are embedded. So network structure matters. The initial configuration of the network determines how it evolves and what structure emerges. So that's connecting the local to the global. And this is only one particular kind of emergent structure. But I think that my hope is that it illustrates the possibilities for ways we might focus both on sort of the details and the particulars of local interactions, while also looking at the consequences for the emergence of global organization. And it demonstrates in particular that we need to move beyond the question of learning biases by themselves in the emergence of morphological structure and typological distributions, and need also to pay attention to the local interactions. Okay, so coming back here at the end of the talk now, just for a couple minutes, to revisit this metaphor, we started with this idea of emergent structure with the audience sort of surrounding street performers. And in some ways, this is a good model. As I said, each person within the audience interacts only with sort of the people around them, and the structure of the circle emerges from those local interactions. But there's also a way in which I think that this is a bad metaphor. One thing that we've seen now is that there are sort of different global structures. So street performers, given enough space, people will congregate around street performers in a circle fairly reliably. But in actual inflectional systems, we find a variety of different kinds of structures, right? Different kinds of networks. And we also see that the way that local interactions happen depends a lot on the context, the network context for those interactions. And so really, it's not always the case that the circle, so to speak, emerges. In fact, we find different kinds of structures emerging in different contexts. Depending on the starting point for those local interactions, the particular structure of particular neighborhoods in the lexicon. And in this way, I think perhaps a better metaphor is in fact Conway's Game of Life. If you haven't seen this, I recommend looking it up on YouTube. So I'm not going to go through the rules of the game, but what's crucial to the game is that all interactions are local in nature. So squares can turn black or white depending on how they interact with other squares around them. And there's sort of a particular set of rules around whether a given square in a particular generation will turn black or white depending on what's around it. But what's really notable about Conway's Game of Life and what it's sort of really known for is the initial configuration determines how the system evolves. In other words, the rules of the game stay the same. So that would be in our metaphorical equivalent. The learning biases stay the same and other functional pressures stay the same. But the sort of initialization conditions for the game matter hugely for the outcome. So we have to pay attention at the very local level to the nature of those interactions. So I'd say that this is a better metaphor in many respects for what's actually going on in morphological systems and the way that we should sort of think about interactions and ways that foxes and hedgehogs can communicate. So Aronoff pointed out that morphological systems vary greatly in the extent and type of their complexity, making morphology a playground for foxes. And I certainly include myself in the foxes category. But I think that foxes have quite a lot to contribute to the ideas and proposals of hedgehogs of the world. Specifically, more precise quantitative tools for describing inflectional organization can offer better insight into how words interact locally, so we can get a view of those interactions in a way that we might be able to talk about in a sort of systematic way in the context of learning biases and other pressures. And ultimately, this has implications for morphological generalization, learning, change, and emergent structure. And we need to pay more attention to these local interactions when investigating typological patterns and emergent morphological structure, and not be too wooed by the hedgehogs of the world and their focus on the learning biases and the pressures separately from the particular input conditions on the ground. So the code for the analogical learner that I showed in the third section, and also for the graph theoretic exploration of inflectional networks that I showed in the second section, are both available from my GitHub page. Here is the links for anybody who might want them. And I again thank the Brazilian Linguistics Association, Berlin, for this opportunity. Thank you very much.
Thank you, Andrea. Thank you for a compelling and very rich, dare I say, brilliant presentation. Speaking as a hedgehog, I learned a lot from it. So we're now at the, and I appreciate all that you did to make it accessible to us hedgehogs. Let me now open the floor for questions and comments and discussion through the chat function. And maybe while we're waiting for some listeners to formulate questions for chat, I'll ask you one myself just to start things off. Going back to your circle metaphor and the Pompidou, I wonder if, as a way of bringing this into, updating it, so to speak, into the present day, in a COVID world, with social distancing, we would have a very different, or we could, in principle, have a very different configuration. And I wonder if you might think of the social distancing due to COVID as a kind of constraint imposed by universal grammar on the, just to push the metaphor further.
Okay, what do I want to say to that? I admit that I was not expecting this question, so I'm sort of thinking about it on the fly as I go. I mean, I think that we are living in a sort of different world, right? We're living in a world that's connected and disconnected in very different ways. And I think that that's its own sort of interesting network question, right?
Yeah,
is how our networks have changed, the ways our communicating have changed, right? I think that it doesn't directly engage right to the question of inflectional networks, which are really thought of as sort of cognitive structures rather than social structures. But I think that there is, I don't know. I mean, it's an interesting, this idea of universal grammar, right, is really an idea of hedgehogs, right? It's a unifying universal pattern, right? And I think that there's been this big push in recent thinking from universal, not even very recent thinking, but a sort of long trend in linguistics of moving away from universal grammar-based explanations and towards functionalist explanations and other sort of pressure-based explanations in linguistic systems, and viewing the explanation for morphological systems and typological distributions in more sort of historical emergent terms. But one thing that really strikes me, and that really was sort of the underpinning of a lot of my thinking in developing this talk, is that that's still very much hedgehog thinking, right? It's still very much about sort of unified understanding and unified approaches to organizing principles of language, right? Whereas by my own tendency, and I think yours, right, I think is to focus on the narrow in a lot of ways, right? To look at the changes in the contexts in which they happened. And so even though there's this sort of shift in modes of explanation, in a lot of ways that shift has not, pre-COVID or post-COVID really sort of led us into thinking about the micro interactions that are happening every time we get morphological change. But I think that we can have the tools for doing that. So I know that's not quite to the point of the question, but
it was really just to
get us started.
to get us started, give you a chance to to expound further on your ideas. Well, I'm not seeing anything in the chat, so let me ask you another question, if I may. The one critique that has often been made of the parent-to-child transmission model for as a way of accounting for language change is that children don't exist in a vacuum. Society isn't chunked into 20-year generational pockets, as it were, and the child ultimately assimilates into the adult world, and exactly how that happens is a complex sociological phenomenon, but it has linguistic consequences. So as I understood your modeling, that isn't built into your model, but could it in principle be, and how would that alter the view of the model?
Yeah, that's an excellent question. So iterated learning has really been a model that's been used primarily, at least in linguistics, for modeling the parent-child transmission problem, right? Where parent and child need to be taken a little bit metaphorically, where it's really a question of more about transmission, less about parent-child, right? Where really what matters is not whether it's really a parent or a child, or even what the generational difference is, but that there's sort of children receiving input, which they then apply learning algorithms. But it's been really focused on this, not in terms of language as a social entity, right? Where we recognize that people will continue to change their speech across the course of their lifetime, where we recognize that people are receiving input from many different generations of people, so they might be getting very different input from very different kinds of people, socially, generationally, etc. Where we can recognize that there's generational, sort of like there's cohort effects, right? Where children want to be similar to people of their generation, right? So none of these things are usually being modeled in the iterated learning environment. It's really been focused primarily on the question of learning biases, okay? And understanding the way that learning biases shape what gets learned. And I think that for me, you're right. So we're doing the same thing. So we're ignoring enormous parts of the problem in a lot of ways. But for me, that makes it, in some respects, all the more powerful to show that what's in the input matters enormously for what is in the output, because the models have been seen as sort of highlighting the importance of learning biases, and not much attention has been paid to what's being learned in the terms of sort of what was in the input structure. And so what I want to sort of show here in part is that the structure of that input matters enormously. Now, that doesn't solve the social parts of the problem, right? But it does show that even put to the uses that are typical for iterated learning models, that we need to be paying even more attention to the structure of the input data at a local level that the metaphorical children in the model are being given.
Yeah, and no, I think that's an excellent answer. You've got to start somewhere, in other words, and maybe if you started with all of the social parameters that you were talking about built into the model, you wouldn't be able to tease apart which ones were most relevant.
Yeah. So I think the ironic thing to me is that this is sort of a hedgehog moment. I think of myself as very much a fox, but this is very much a hedgehog moment, in that I'm sort of ignoring lots of the issues and details that surround what we know about language learning, right, in order to focus on sort of a unified mode of explanation.
Yeah. Great. Well, I'm still not seeing anything in chat. I don't know. I think you covered everything so clearly.
Yeah. If nobody has any questions, I suppose that we can, go about our day. But
well,
I appreciate this opportunity.
Let me ask one last question, or
Sure.
give you one last opportunity, and to speak further, and give others one last opportunity to chime in. I thought that perhaps for me at least, the most significant takeaway was what you said in slide 51. You don't have to show it again, but it was that pressure towards similarity is not the same thing, is not equal to pressure towards simplicity. And I just wondered, I thought that was a very nice formulation, but also very deep in some respects. So I just wondered if you could expound on that a bit more.
Yeah, this is a really directly connected to this notion of local generalization,
Yeah.
right? So I think that in previous presentations of this work, people have frequently have thought that what we are modeling is a pressure towards simplicity, essentially a pressure towards classes collapsing to high type frequency classes, which we might think of as a kind of regularization.
Yeah.
And there's a lot of work out there in the field that certainly thinks that regularization is a kind of a pressure in language learning. But actually, because in the model, people are simply trying to predict one inflected form at a time, not entire classes, it's entirely possible for words to sort of fracture and become as, more morpholexically specific, right?
Yeah.
Because it's possible that, the pressure towards similarity on word inflected form A, paradigm cell A, will push it in this direction because of its neighborhood. But in paradigm cell B, maybe it'll push it in that direction because of its neighborhood. And so what was a single class now sort of shatters into two different classes. And so I think that this is really important, right? It's a function of this idea that the pressure is not towards shifting classes. The pressure is really towards sort of looking at similar words and trying to make a prediction. And about what a particular form will be in a particular local context, and even within a given lexeme, those pressures the neighborhood may suggest different answers, right? And so I think that this idea that there's a pressure towards similarity and not a pressure towards simplicity is a direct sort of outgrowth of viewing morphological generalization as happening in these very local contexts.
Yeah. And Rich John and I talked about diachronic fragmentation, to use the exact same etymon as your fracture. Yeah,
exactly.
Great. Well, thank you. This has been lovely. I don't see any comments in chat. I think because you covered things so clearly, how could anyone, anyone have
thank
anything
you,
to
Brian,
say?
for your very stimulating conversation, very stimulating questions, and thank you to the Brazilian Linguistics Association for this opportunity to give this talk.
Great. All right. So we close this session, but end on a very high note. Thank you. Thank you, Andrea.
Thank you.